Hi, my name's Joe Tennant. I'm the VP of Software Development at Seven Signal, and I want to talk to you about a case study about our move from Apache Flink to Apache Pinot. And I'm going to frame this study with a discussion about managing design decisions or trade-offs. When considering how to talk about the study, I was thinking about how I spend a lot of my time during my career. And I've been a solo dev, I've been a team lead, an architect, et cetera. We've all worn many hats. And what I thought about was I spent a lot of my time considering the trade-offs of these decisions. And every decision has a trade-off of some sort. All levels of software development involve trade-offs. Should I use a functional class? Should I use a new class? Should I use a streaming processing system or batch processing, a relational database, or something else? Engineering in general is all about considering the impact of the choices we make. Ultimately, we're trying to meet all the requirements of the system that we're building the best we can. We're constantly balancing competing factors. In order to get this, you have to give up that. For example, if you want to increase the performance of your application, that's going to come with increased costs. You have to launch more nodes. You have bigger servers. Maybe you want to introduce caching. Maybe you need to rewrite part of the application. Another example would be to introduce flexibility, you might have to introduce complexity. Microservices are an example. Microservices are very flexible. Different parts of the system can be customized. You can use different languages, different tools, but they come with complex hosting requirements. Additional troubleshooting challenges operationally. You might need to introduce a messaging system, auditing tools, APM tools, and so forth. Furthermore, we're often trying to balance conflicting requirements. These are requirements that have an either or sort of implementation. To optimize for one requirement, you have to compromise that other requirement. And a very common example would be to optimize your writes of large volumes of data into a database, for example. You often have to compromise the read performance of that database. You might decide to use table copies or disable constraints or remove indexes, but these compromise transactional integrity or they slow down read performance. Maybe you want to use a different data store so that you can ingest data quickly, but this might come with constraints on how data can be read. You don't have the normalization you might have had before. You can't use table joins, or maybe you decide to use a NoSQL tool when your dev team relies on SQL skills. Dealing with these trade-offs often requires careful consideration of priorities. What are your primary use cases? Can you shift trade-offs? Can you trade one compromise for something else? For example, if you need to ingest large volumes of data and have fast reads, you might introduce processing delays, and that's a way to shift trade-offs. And finally, we have to deal with products and how they change over time. No good design meets the user or survives meeting the user. Users are going to use your system and their needs are going to evolve. Things are great now, but you will get new customers. You might get really new important customers and their needs will be different. Furthermore, systems that work really great in early stage products become limited during periods of growth. Your scalability requirements will change. Speed to market might hamper your ability to compete in larger spaces in the future. So how do we manage trade-offs? The very first thing we need to do is we need to be able to identify them. You need to know the impact of the decisions you're making, and you need to be deliberate about those decisions. Some choices might seem really obvious, but don't just select them. You need to understand what your options are going to be. Probably most importantly, you need to communicate this. Don't make decisions in the vacuum. And I don't mean a vacuum of yourself, but even your team. You need to talk with your stakeholders and you need to collaborate. Business and product requirements often involve subtlety, just like technical decisions do. And what you want to do is work with these teams to make these decisions together so that they can be complementary. Oftentimes, these requirements are flexible. Some requirements can be adjusted, removed, or changed just to maximize the whole design. You want to find the best balance of the system. Finally, you need to document the decisions that you made. You need to write them down, especially because decisions will become this complex web of interactions. Future team members are going to want to review these decisions to remember why they were made. And you might be that person in the future. For example, why did we decide to use MongoDB 5 years ago? And in my experience, it doesn't really matter how you document these decisions. You just need to document them. You can update your requirements document. You can write a technical specification. You can use ADR records. It's more important that you do it than how you do it. The other thing you should do is consider different types of trade-offs. We're familiar with technical trade-offs. Query performance versus data timeliness. I talked about this trade-off a little bit earlier, and it's actually going to be part of the case study I'm going to talk about in a minute. Or stream processing versus batch processing. A nightly job or a micro batch could be much less complicated than a stream processing system. And some technical decisions really have non-technical consequences as well, and we need to consider those. What are those costs of the new technology? I don't mean just money costs, but does your staff have expertise? Do you need to acquire more training or hire people with certain skills? What about operationally? Your operational staff needs to know how to run these systems and keep them tuned. Or your choice might be adding complexity to a system because it's different. It's a one-off. If you have to add a batch process because it's really easy, but you have this whole architecture of stream processing, it might make sense to integrate it with that existing architecture. Finally, is this the latest and greatest thing? Is the technology well established? Is your desire to build something really cool biasing your decision? You need to consider those sorts of things as well. Some other things to think about. Timelines. Those are definitely trade-offs. I know they always seem fixed, but those are things that can be negotiated. You need to be honest and you need to collaborate with your team. You also need to understand the business drivers. What are you trying to build and why are you building it? You have non-functional constraints as well. I mean, you ultimately need to build this thing. So you need to understand what your costs and overhead are, and the business also needs to know this. Go back to collaboration. Do you have specific talent? What are the operational needs, security considerations, et cetera? Also consider how scale affects your trade-offs. Sometimes a complicated system is actually easier to run in production than it is to run in a development environment or a research environment. A whole cluster might be really hard to manage by a small dev team, but it's totally reasonable at scale. Don't forget to document. The team, the business and the technical team, collectively decide to compromise on a decision in order to maximize your speed to market, and the team knows that this is going to require some reworking in the future, write this down and why. What are the decisions that were made and who made those decisions? Because in the future, when you meet those scalability limits and you're asking for more time, money, and resources, you can point to this record of deliberate and collaborative decision making as to why you're there. You definitely want to avoid having a deliberate technical decision in the past appear as a poor technical decision in the future. Remember, your team decided to make that trade-off. When you're thinking about trade-offs, consider what's irreversible. A data partitioning scheme might not really be changeable after you've processed large quantities of data. Dropping a field now might not be recovered in the past. If you really need that date field, when working in a small company like Seven Signal, speed to market is critical. You might be constrained with staff. You might limit the amount of research and evaluation you can do. So you might want to consider sufficiency to make decisions. If the decision you're trying to make is viable, you might just have to go for it, even though you can't evaluate all possible alternatives. And remember to document that in and of itself is a trade-off. So that brings me to a case study that we'll talk about. So a little bit about Seven Signal really quick. Seven Signal provides digital experience monitoring solutions specializing in Wi-Fi and network performance. Our platform includes sensors and agents that collect and monitor Wi-Fi and network information. We provide this inside in perspective. We look at the networks from the client's point of view. We help detect and diagnose connectivity issues, network disruptions, and overall performance. And we're designed to monitor continuously. So we provide a view of the network right now, or last week, or last month. So the users can troubleshoot issues that are happening now or later and proactively address systemic problems. Like I said before, Seven Signal is a relatively small company. We don't have a large development team, and we don't have a dedicated data processing team. And our operations team is not very large. And this is a real consideration when we're thinking about how we want to implement different solutions. We have hosting considerations. We have to consider the skills of the team. We have to consider what projects we're currently working on. And recently, in one area of our platform, we observed a shift in how users were interacting with the system. This really prompted us to reevaluate the trade-offs that we had made previously relating to how fast we ingest data and how fast the application performs. In the end, we ended up transitioning from using a stream-based pre-processing platform to a query time model using Apache Pinot. And I'm going to talk a little bit more about that right now. The Mobile Eye part of our solution is designed to capture network and Wi-Fi information from software systems, software agents running on laptops or handhelds like Android devices. And this provides that client view of the network, both network connectivity and network quality. This information is then presented in a dashboard designed to show this data across a variety of different dimensions. For example, was the device experiencing interference related to a network condition yesterday while in a conference room? This might be a specific device. We might be looking at the raw data that was measured at a per minute level, or we might be looking at roaming issues across different adapters and drivers. And this might be a monthly or a weekly roll-up of this information. Certain drivers and adapters will perform better or worse when it comes to roaming on a network. For a whole building or whole location, we can show how the network is performing in an aggregate for a whole month or a particular day. So to optimize for performance and responsiveness, our data is pre-processed into specially built tables designed specifically to support the UI. Our time series data is bucketed into 15-minute and 120-minute segments, depending on the time range that the user selects. This means that varying volumes of data, for example, multiple devices, different endpoints tested, they're converted into stable time-based records. And users can adjust filters and drill into different data sets, and the performance is consistently good for them. Let's dig into this a little bit more. Since our solutions continually monitor the network, there's a continuous stream of incoming data that we need to deal with. We have Kafka streams in place that receive data from our agents, and we have Apache Flink jobs that produce these summarized records. There's something like 35 million metrics per hour that we're processing and loading into relational databases, in this case, Postgres. And as I mentioned before, by pre-processing these metrics or summarizing them, we can ensure predictable performance. The number of contributing devices and the volume of data can be aggregated into a single result. So in this example that we're looking at, you can see these little yellow and blue blocks are being aggregated into a single record that are loaded into the database. The number of yellow blocks, for example, doesn't really matter. We're always outputting a single record. This is the bucketing or aggregation. This tumbling window that we talk about, this is that 120-minute period or the 15-minute period. Now, in the screen capture that you can see over on the right, what we're looking at is we're looking at network performance for several locations or facilities across a 7-day period. And each one of those little segments, you can kind of see a little gray slice under there. That's the highlighted segment. That represents a 2-hour period. And the way that we're pre-processing our data, we can render hundreds of these locations in 500 milliseconds or less, regardless of the number of devices testing or how much data contributes to those segments. It's very fast, it's very efficient. To look a little bit more at the database is structured specifically to drive the charts and the views in the application. It's not an ad hoc reporting system. And you can see in this example, the SQL that we use to query that data, it's very simple. And the database is partitioned by day. That makes it easy to manage, and it makes it easy to truncate data after that data retention period has exhausted. The incoming records that are written in roughly chronological order. So as the Flink job window closes, those results are written to the database, and then they're being clustered to pages efficiently by time. Queries with specific time ranges can be satisfied without excessive spanning or page reads. Remember, when we're talking about trade-offs, we're using a well-known relational database. It's very mature. Our application team can use all the SQL tools that they're familiar with to access the data. The queries are very easy to write, and they're very easy to understand, and that's a major benefit for us. And now comes the but. So what we're learning from our customers is that more and more they want to use the tool to do real-time analysis. They really want to know what's happening right now with these agents. Oftentimes they want to load an agent on a device and they want to start seeing that data right away. Now we optimize the system to pre-process that incoming stream of data so that we can have consistent query performance. And this was a deliberate decision. This was a trade-off that we made. We traded the application performance for the currency of the data. Those 15-minute summarized records we were talking about, they're not written into the database until after that window closes. And in fact, we allow for some extra time to handle late arriving data because there's always late arriving data. And what this results in is that data doesn't appear in the application for like 20 minutes or so. And that 20 minutes is not right now, according to our customers. So now we're in this situation where we need to think about the trade-offs that we made. So there were possible solutions that we considered. It's relatively easy to have Flink do upserts of these records during the tumbling window. It's not a fundamental change to our processing system, but this resulted in severe data fragmentation, and it significantly slowed down our queries, especially when spanning partitions. We considered trying to read the current period of time directly from Kafka or S3, where the raw data is ultimately stored. But this was considered awfully complicated. To integrate into the existing system, we would have two ways of accessing the data that have to be kept in sync. It's operationally complex as well, and it has performance implications of its own. So that led us to reevaluate the entire processing pipeline. And that's what we did. So what we ended up doing is we ended up considering the requirements and the trade-offs that we needed to have, or the ones that were working in our favor. We needed to have the fast query performance. We needed to have real-time data availability, and we wanted to retain that SQL interface that our application development team really enjoys. And we looked at the landscape of tools designed for processing and managing time series data, and a lot of these tools had limitations that didn't necessarily work for us. For example, you can only aggregate in certain ways. A lot of the tools were designed for data warehousing or running business style reporting tools and not really running a customer facing application. I kind of already spoiled it on the slide, but we ended up choosing Apache Pinot. And this tool didn't exist when we designed our original data processing system, but it really is a perfect fit for our use case. A couple quick highlights. Pinot has a native integration for Apache Kafka, so that made integration easy for us. Query performance is very fast. It comes with a lot of indexing options that allow us to optimize. Data is written directly to segments from Kafka, so that data appears immediately in our system. And it comes with a SQL interface, and that keeps it easy for our application development team. Dictionary storage for low cardinality data, which we have a lot of. For example, our device types, platforms, locations, they're low cardinality. It really has all the bells and whistles. It's really designed specifically to do what we're doing. And if you consider Pinot a black box or a wine glass logo on your architecture diagram, it really makes the architecture simpler. The data, in our case, will now moves from our agents into Kafka and then into Pinot, and that's it. Very simple. The aggregation that we're doing, it really happens at query time. And if you look at the example on the screen here, you can see that the queries aren't much more complicated than they used to be. But of course, there are trade-offs. Pinot is new. It's only 2 or maybe 4 years old, depending on how you count that. And hosting Pinot is very complicated. With brokers, we've got minions, we've got other things. It's specific storage needs, scalability needs, and so forth. And we need new skills in order to know how to effectively tune and administrate this new tool. So let's dig into a little bit of the details of how we did this integration, and I'll talk about those trade-offs in a minute. Pinot is really designed to handle aggregation-heavy queries over large volumes of data, especially time series data, and this is exactly what we do. So specifically, what we did to optimize our implementation is we use a lot of inverted indexes for our low cardinality fields. We have a lot of those. This allows Pinot to quickly access and filter predicates. We also use range indexes for our timestamps. This is an optimization for those between style queries. And another thing we did related to range indexes is we took our timestamps and we pre-calculated buckets. We basically truncated the timestamps into a bunch of different fields. For example, we would take a timestamp in its raw form, which would be specific to the millisecond, and we would store that in a 1-minute truncated form, a 15-minute truncated form, a 100-minute, 20-minute truncated form, and so forth. And what this allows it allows Pinot to do aggregations and searches very quickly because we lowered the cardinality of those fields. And we're exploring some other optimizations like StarTree indexes for report style queries, aggregations that occur over several dimensions in a long period of time. And we're looking at geospatial indexing and vector storage for future projects. So go back to those trade-offs I talked about. Moving to any new architecture introduces new trade-offs. And some of these are clearly advantageous. Instant data availability, we talked about that. That was definitely a requirement. We can now make data real time in our application. Consolidating our data processing and storage into a single system, we simplified our architecture by having a single black box, if you will, for that. We don't need Flink jobs for processing incoming data. Now, we use Flink for other stuff, but we don't have to use it for this purpose. And we retained that low query latency that we needed. There's a whole reason we built the system in the first place. The old system was to have this fast user interface, and Pinot retains that capability. And more to the point, Pinot brings a lot of different ways to optimize those queries. We're not boxed into one style of index or one style of querying this data. We have a lot of options. And of course, we talked about complex hosting requirements. Deploying Apache Pinot is not a trivial thing to do in a production environment. You need a whole new host of skills to maintain and administer Apache Pinot. Additionally, we need to make sure that we're tuning the system properly, that we can tune our queries, use the right indexes. So another set of new skills. And Pinot is young. It's really a new tool, and we have run into bugs. We've had to implement workarounds. We continually get updates to the system. That's something that is a cost that we are accepting. I don't have it on the slide, but as a bonus, Pinot is a clustered system, which means certain statistical functions are estimates. And these are important to know when you're building a system and presenting data to your users. So, since we're always managing trade-offs, we had all this hosting complexity. We had the lack of certain specialized skills, and we decided to accept these by using Pinot. So we looked at a way to trade these for something else, and then what we decided to do was partner with StarTree as our managed service provider. And what this allowed us to do is shift our need to host and optimize Pinot to StarTree. And we were able to get our evaluation off the ground quickly. We were able to get into production, and we gained a lot of confidence in our solution because we have the skills available to make it successful. And at Seven Signal, we're a small company, so we often use MSPs to accelerate what a small team can accomplish. There's trade-offs here as well. Cost, using an MSP is always going to cost more than self-hosting. And to some degree, there's some lock-in to the vendor. But StarTree has been a great partner, and we're very happy with those decisions. So to cap it off, what are some of the key takeaways? Managing trade-offs, it's something we always do. It's something we need to do deliberately during our design phase and during the life cycle of our product. Remember to identify, communicate, and document these decisions that you make. And don't be afraid to reconsider a past decision. Market forces change and product directions change. Trade-off decisions that you made in the past, they might have a different calculus now. There might be new tools available. If you have the documentation in hand that you made before, you can discuss these new changes without any fear of being blamed for past decisions. Also consider partners or bringing in experts to help mitigate certain trade-offs. They can shift your technical burden to something more like a financial cost or a different kind of burden. So to cap it all off, this presentation was about how and why 7Signal converted our Flink-based stream processing to Apache Pinot. And this might not be the right solution for you. You need to consider your trade-offs. And remember, whenever you're reading a use case or a white paper, be sure to understand what the choices are that they're making and the trade-offs that they're making. That may or may not apply to you. And that's the presentation. Thank you.